Okay. Good evening, all. So, welcome to the live session for the course Characterization of Construction Materials. Today, we'll have the discussion on the week 7 content, which was taken by Professor Manu Santanam, mostly based on the microscopy. There was different topics which were discussed related to the optical microscopy, scanning electron microscopy, etc. So, let me try to share the screen, and without further ado, let's start the practice questions. Yeah. Is the screen visible to all? Can you confirm in the chat box?
Yes, ma'am, it is visible.
Yeah, thank you. Just a minute. Okay. 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 So let's move to the first question here. It's related to the microscopy content. Arrange the type of microscope in the increasing order of the detection limit. We know that we use different types of microscopes like transmission electron microscope, optical microscope, then scanning electron, etc. So, what is the increasing order of their detection limit? Option A, compound light microscope detects uh, cannot detect as much as the scanning electron. It cannot detect as much as transmission electron microscope. So here, increasing order of the detection limit. This means that the option A means that transmission electron microscope can detect more than scanning and compound light microscope. Okay. I have received a few responses from KPC Rao, Pratiksha Patil, and Smita Bhagwat. All says A. Is there anyone else who would like to respond? So here the options are between scanning electron microscope, transmission electron microscope, and compound light microscope. Okay, let's move to the correct answer. So the correct answer is option A, as rightly told by those who have responded in the chat box. So here is a unaided human eye detection limit. So compound light microscope lies a little further than the unaided human eye, whereas scanning electron microscope can detect a little more smaller objects than the compound light microscope, whereas transmission electron microscope can even detect up to zero point 0.1 nanometer scale angstrom scale particles also can be detected by transmission electron microscope. So the detection limit of transmission electron microscope is much greater than that of scanning electron microscope and that of compound light microscope. Okay, let's move to the next question here. Given below is a block diagram of a transmission electron microscope. Identify the unlabeled component. So this is just a flow chart which shows the process or different components of a TEM, transmission electron microscope. What is missing first? So something, then condenser lens, then specimen, then comes objective lens, and then the projection lens. Is it an electron source, scanning coil, light source, or objective lens? Okay, I have received a response like C and A. Okay, anyone else? Pratiksha goes with A. Others, just respond. Let it be right or wrong. It doesn't matter. What matters is that you should understand the concept by the end of this class. That's it. Okay, Mehna also goes with A, electron source. Smita also goes with A. Okay, so let's move to the correct answer. Correct answer is option A. So in the case of light microscopy, light source is the correct answer, option C. But here the question is about a transmission electron microscope. So in the case of a transmission electron microscope, first of all, there has to be an electron source. That is a primary necessity. Then comes the condenser lens. Then in between there's specimen. Then comes the uh, projection lens. Okay. Let's move to the next question. In scanning electron microscope, the electrons interact with the specimen surface, where in transmission electron microscope, electrons pass through the sample. State true or false. So, in the case of a scanning electron microscope, the electrons just interact with the specimen surface. It doesn't pass through. Whereas in the case of transmission electron microscope, they do pass through the sample. What about others? I have received two responses. Okay. Okay. So the correct answer is option A. That is a true statement. So in the case of scanning electron microscopy, they cannot pass through the substance or the sample. It just interacts with the surface, meaning it can either get scattered by hitting the sample, or it can undergo, you can hit the sample and make the electrons undergo transition between orbits. That can happen. So these are known as the interactions. So these can happen in the case of scanning electron microscopy. Here it's not passing through. But in the case of transmission electron microscopy, that's not the case. Electrons can pass through the specimen surface. That is the case of transmission. As the name suggests, it is transmitting the electrons through the sample. So the statement is true. Okay, let's move to the next question here. Which of the following is used for finer polishing as part of the specimen preparation for scanning electron microscopy? Okay, so in scanning electron microscopy, different types of interactions are present. Like we can do a secondary electron imaging, or backscattered electron imaging, or something like X-rays can be used for imaging. In the case of backscattered electron imaging, what happens is that we need a very polished, smooth surface, specimen surface. For that, we need to polish the surface a lot. It can be a coarse polishing initially. That means it's not that smooth, but it is doesn't have much of a undulations. But then there is something like fine polishing also, where the specimen will be polished to a greater extent. It will be very smooth. The surface will be very smooth. So what is used for the finer polishing of the sample in scanning electron microscopy? Okay. So KPC Rao and Pratiksha, they have told it's diamond spray. Okay, I'll wait for a few more seconds for the others to respond. What about others? Mehna, Javed, Smita. I'm just calling out the names. Jeff, it's familiar to me. Rutuja. Okay. So Mehna also goes with C. Okay, let's try to look at the answer. So the correct answer is option C. We use carborundum and also sandpaper, but that is for the coarse polishing. So first level of polishing, which doesn't need very fine level of polishing, that can be done using carborundum material or a sandpaper. But for a finer polishing, we need diamond spray. So let's move to the next question then. Choose the lubricants used in the finer polishing of specimens for scanning electron microscopy. We need lubricants. while polishing the specimens. What is used as a lubricant in the final polishing? Last question was what is used basically for polishing? That was diamond spray. Now, what is a lubricant used there? Is it isopropyl alcohol, ethanol, or grease? I'm waiting so that someone will respond in the chat box. So, what is used as a lubricant in the case of final polishing of specimens for scanning electron microscopy? Before the end of today's session, if you can please explain the question 6, 7, 8, 9 of assignment 6. Okay. What was assignment
Ma'am, good
6?
evening, ma'am. Actually, all of them are related to one question only, ma'am. That the data was given, and we had to identify the isomers, isotherm, and
Okay,
draw.
okay, okay. Yeah, I got it. I got it. Unfortunately, it was not me who prepared it. It's better if you ask Neela. Can you do that?
Okay, ma'am. Because the numerical part we couldn't solve. I couldn't solve it. The first part I was able to identify the isotherm, but
Okay,
how to
okay,
go
okay.
about the other part of the numerical, ma'am.
It was
Uh,
discussed in one of the Friday session.
it was discussed on Friday session. Okay, that is okay.
Yes.
Doesn't matter. It will be discussed in the next Monday session. Okay, no?
Hmm.
Is that okay, sir?
Yes, ma'am. It's fine, ma'am. I'll go
Yeah.
through. Actually, I think I've missed out on the Friday part, ma'am.
That is, I mean, it doesn't, it's not compulsory that you have to attend all the three sessions. I mean, I know it's difficult, but it's okay. We will take, okay, 6, 7, 8, 9, we'll consider and then we'll explain it in the Monday session. Okay. So let's move to the correct answer for this question. So the correct answers are B and C. Ethanol and grease are used as lubricants. Isopropyl alcohol we cannot use because of faster evaporation rate. Okay, let's move to the next one. The limiting size above which the specimen section cannot be used for thin section microscopy is 75 microns, 30 microns, 5 microns, or 50 microns. Sometimes we use very thin sections in order to get the several features in the light microscopy. So, what is the limit up to which, above which we cannot use the thin section? What is the limiting size? 75, 30, 5, or 50? Okay, we received two responses. What about others? Okay, so let's move to the correct answer. Correct answer is B, 30 microns. I don't think it requires further explanation. So 30 microns is the maximum size you can use for the thin section microscopy. Okay, so let's move to the next question. So, in scanning electron microscopy, there sometimes occurs the process known as charging or the phenomena known as charging. So, what is charging in scanning electron microscopy? Charging is the penetration of electrons through the sample, causing distortion in the obtained images. Or, it is the process of transforming a non conductive sample into a conductive sample. Or, it is the accumulation of electron on the surface of non conductive samples, or it is a generation of momentary electric current within the sample. So, what is charging in terms of scanning electron microscopy? Okay, received, I think, only one response. Okay. Okay, let's move to the correct answer. The correct answer is option C. So, what happens is that when you use non-conductive samples, like anything other than metals, basically, metals, we all know it's conductor, so this problem doesn't occur. But if you use construction materials like cement or lime or anything which is non-conductive, what happens is that the electrons, when it falls from the scanning electron microscope, it gets accumulated on the surface. So that process is known as charging, and it occurs when the samples are non-conductive. Okay, let's move to the next one. Now, what is a sputter coating? It is a process of coating the samples with molten metal for the penetration of electrons through the sample, or it is a surface coating of the samples with gold palladium to make the surface conductive, or it is a coating of the sample surface with IPA to prevent the accumulation of electron on the surface of non-conductive samples, or sputter coating is the epoxy impregnation of the sample to retain its microstructure or its structure. So, what is basically sputter coating? So, this is one of the processes which happens in the case of a scanning electron microscopy. So, what is basically a sputter coating? Okay, so KPC Rao goes with option B. Pratiksha also option B. Who else? What about others? Okay, Mehna also goes with B. Okay, so the correct answer is option B. It's a process of gold coating the non-conductive sample surface with gold and palladium, such that the surface becomes conductive. It's not necessary that the electrons should pass through the sample, because, as we rightly told before, in the scanning electron microscopy, the electrons don't go through the sample; it just interact with the specimen on the surface or a little distance, micron distance into the surface. So that interaction volume might change depending upon what type of interaction it is, but it's not necessary that the electrons move through the sample, just penetrate through the sample. Only the surface need to be conductive. So that can be done by coating the non-conductive samples with gold and palladium, such that the surface can become conductive and the charging can be avoided. Okay, let's move to the next one. Now, again, it's about sputter coating. So, sputter coating with dash results in a pink violet tinge on the sample surface. So, we can do sputter coating with different materials. So, which of the following, when coated into the sample, gives a pink violet tinge? Is it carbon, chromium, gold palladium, or magnesium? Okay, Pratiksha and Smita. The goes with C. What about others? Smita goes with C. Okay, who else? Okay, Mehna also goes with C. I think this is a fairly easy question. So this is the image, which is also a snippet from the slides. So here the sample is coated with a gold and palladium layer. So this gives a pink or violetish tinge to the surface. Okay, let's move to the next question. Now choose the correct statements regarding sputter coating of cementitious samples before introducing them to scanning electron. So before introducing the cementitious samples, we have to sputter coat. Why? Because we have to make the surface conductive and thereby avoid the charging. So option A, sputter coating of the sample with carbon brightens the sample surface. Option B, sputter coating must be done at vacuum. Then option C, samples need not necessarily be completely dry while sputter coating. Option D, sputter coating converts the entire non-conductive sample into conductive sample. Then option E, sputter coating is not necessary for ESEM. Okay, Pratiksha goes with D and E. Waiting for the others to respond. Please do respond in the chat box. Even if it is wrong, even if it is partially correct, it is totally fine. Javed goes with E. What about others? D, E. Others, please do respond fast. It's about sputter coating, which is to avoid charging of the non-conductive samples. Okay. D and E. Okay, I think we have given enough time for the responses. So the correct answer is option B and E. See, what happens to D? It converts, sputter coating converts the entire non-conductive sample into conductive sample is a wrong statement because we are just coating it and we are not converting anything, not the entire sample into conductive at least. We are just making the surface conductive. So the option D is wrong. Why option B? Sputter coating must be done at vacuum. We generally, when if you are doing scanning electron microscopy, you can understand that if you book a slot, we have to go like 10-15 minutes prior to the our given slot timing, and then we have to apply vacuum. Give the specimen and keep the specimen at the sputter coating vessel, then give the vacuum. It takes like 5-10 minutes to attain the vacuum, and then coat with the gold palladium or whatever material for sputter coating. So find the first ever step is to make the system into vacuum and then apply the coating. So sputter coating has to be done at vacuum. Now option E, sputter coating is not necessary for reason. That's a true statement. For environmental SEM, it is not necessary to sputter coat. Now, sputter coating of sample with carbon, it actually darkens the sample surface. So option A is wrong. Option B, as I told, it's correct. Then option C is wrong because it has to be completely dry while sputter coating. Then it cannot convert the entire sample into conductive sample. Then option E says that it's not necessary, which is a true statement. So the correct answers are option B and option E. Okay. Let's move to the next one. The process by which light changes the direction as it passes from one medium to another is known as. It's like basic physics question. It's like very general basic physics question. What is the process by which the light changes its direction as it passes from one medium to another? We have done like lots of experiments in school by keeping pencil on water, etc. So, what is the process by which the light changes the direction as it passes from one medium to another? Okay, so I received only three responses. What about others? Like, where is Mena, Javed? Who else? That's it. Pratiksha, Rutuja. Rutuja, are you there?
Yes, ma'am.
Yeah. Okay. Okay. So the maximum goes with C, and the correct answer is option C. So here the refraction is a change in direction from one medium to another. Light bends and it changes its direction as a medium changes. So that is known as refraction. So in that context, let's move to the next question. Assume a very thin lens using the lens maker's equation for the thin lens and find the focal length when the distance of the image is 50 centimeter and the object is kept 40 centimeter away from the lens. Consider that the image forms on the same side as that of the object. So you know what is lens maker's equation. You are asked to find the focal length when distance of the image di is 50 and distance of the object do is 40. So you have di and do. Now find f. Pratiksha goes with C. Others? I'll give one more minute. Anyone else? Okay. I don't think this is a very difficult question. Please try to solve it out. Okay. Okay. So this is the lens maker's equation. The correct answer is C. It's I don't need to solve it out. It's just 1 by f is equal to 1 by di plus 1 by do. Di and do are given to you. Di is 50 centimeter and do is 40 centimeter. So 1 by 50 plus 1 by 40, that will be 0.045, I guess. So 1 by 0.045 will give you 22.22.
Ma'am, can I ask one doubt here?
Yeah.
Here, since it is said image forms on the same side of the object, we are plus. If it is on the opposite side, then the equation will be changing to subtraction.
Yeah, that will be changing. That is why
That too,
this
here instead of addition, this subtraction formula will be
subtraction
applied.
will, yeah,
1 by f
because,
is equal to 1 by di minus 1 by du.
yeah, that is depending on the direction in which you take it.
Okay, ma'am.
So that is why the last line is important, that it forms on the same side. Okay, so let's move to the next question. Find the magnification of lens 1 in a compound lens system having lens 2 of magnification 3 and the combined magnification of 9. So you have two lenses in a combined system, lens 1 and 2. You have to find the magnification of lens 1. Lens 2 has a magnification of 3 and the combined magnification is 9. Okay, so I received one response, which is B. Okay, I think it's a fairly easy question. Yeah, so the correct answer is option B, because the combined magnification is a product of individual magnifications. So here the combined magnification is 9. One magnification is 3. So 3 into x is 9. So x is will be 9 by 3, which is also 3. So here the lens 1 has a magnification 3 and lens 2 also has a magnification 3. Let's move to the next question. In the previous question, which of the lens is likely to provide a higher depth of field? Lens 1, lens 2, or both have equal depth of field? Okay, let me move to the correct answer. The correct answer is C. Higher the magnification, lower the depth of field. Here, both of the lenses are equal and they have same magnification. So, which means that they have an equal depth of field. So, move to the next question. Choose the auxiliary component which is placed within the optical path and can cut off the light vibrating in certain undesired directions. So, light has a particle nature and a wave nature. It can vibrate in all directions. So, if you want to cut down the vibration in one direction, what will you use? Is it a projection lens, illuminators, polarizers, or scanning coil? Projection lens, illuminators, polarizers, or scanning coil? Okay, let's move to the correct answer. Correct answer is C, which is polarizers. Just they are those equipments or components which can cut off the vibration of light in some undesired direction. Okay, moving to the next one. See, there are two optical microscopes, A and B. The aperture size of those both the lenses are same. Though both the microscopes use visible light, microscope A has a additional blue filter and B has additional red filter. Choose the correct statements from below. So you have microscope A and B. Only difference between A and B is that A has a blue filter and B has a red filter. Okay. Now, which of the statements are true? Microscope B will have higher resolution. Microscope A will have higher depth of field. Microscope A will have higher resolution. Both the microscopes will have the same depth of field. Then microscope B will have higher depth of field. So it's all a game of resolution and depth of field. The only difference between uh, A and B is the filter. A has a blue filter, B has a red filter. Okay, I've got C and E. Okay. You have to basically relate resolution and depth of field to the wavelength of the light. What is the wavelength of blue? What is the wavelength of red, etc. Okay, let's move to the correct answers. Correct answers is C and E. So here, resolution is D equal to 1.22 lambda by 2 into aperture size. So here this is same. So only difference is lambda. Red has a higher wavelength. So when B has a red filter, the numerator D or the numerator of D will be higher for microscope B. When D is larger, that means that the resolution is not so good. We need D as minimum as possible. Blue has a lesser wavelength, which means that D of blue will be lesser than D of red, which means that one which is having a blue filter will be having a higher resolution. I don't know whether I should explain again. So this resolution, this is D. For higher resolution, we want minimum D. Remember, they have to be, D has to be minimum. So for D to be minimum, we want lesser lambda. Out of red and blue, blue has lesser lambda or wavelength than red. So whichever microscope using a blue light will be having a minimum D and hence a higher resolution. So definitely microscope A will have a higher resolution. Now depth of focus. Depth of focus is lambda by Na square. So again here is a game between depth of focus and wavelength. So wavelength is higher for red, hence microscope B uses red filter and hence the microscope B will have a higher depth of focus. Lambda is higher for red filter. Red filter is used in microscope B, so B will have a higher depth of focus. I hope that is clear. For resolution, we need D minimum, and for depth of focus, we need maximum. Depth of focus higher is when the lambda is higher. Okay, so let's move to the next question. So again, there are two optical microscopes, A and B. Same magnification, no other difference. Only difference is that A uses air lens whereas B uses oil. It has an oil in between. Choose the correct statements from below. Both are same. Only difference is the presence of oil in microscope B. So microscope B will have higher resolution. Microscope A will have higher resolution. Both the microscopes will have same numerical aperture. Then microscope B will have higher numerical aperture. So which are the correct statements? Excuse me. No response yet. Okay, let's move to the discussion then. So the correct answers are option A and D. Why? Because here we are using the same lambda everything. Only thing is numerical aperture changes. As refractive index comes in the picture of numerical aperture, when oil is there, then the numerical aperture will be much higher, which means that the denominator will be much higher in the case of the lens which uses oil, that is microscope B. So microscope B will have a higher denominator here, which means that D will be minimum, which means it has got a higher resolution. So microscope B will have a higher resolution. Then option D, it has numerical higher numerical aperture. It is evident because it has a additional element of refractive index of n. Because oil is being used in on microscope B, there is a refractive index coming into picture, which increases the numerical aperture, which in turn decreases D, which results in a better resolution or higher resolution. So in this case, B has higher resolution and a higher numerical aperture. Let's move to the next question. It's a true or false question. Reflected mode can be used in optical microscope when the sample is denser, and the transmission mode can be used when the sample is transparent. So there are different modes in which the microscopes work, optical microscopes work. It can be in a reflected mode or in a transmission mode. Excuse me. Reflected mode can be used when the sample is denser, and the transmission mode when it can be used when the sample is transparent. Okay, so the correct answer is A, because in reflected mode we want a denser sample so that it can hit and reflect, and all the features are evident because of the density difference, etc. Whereas it's evident that for it to be transmitted, for the light to get transmitted, the sample is better if it is a transparent material. So the correct answer is true. Let's move to the next one. It's a match the following, fairly easy one. So on the column 1, lens defects are shown, and on column 2, the features of these defects are shown. So the defects are astigmatism, chromatic aberration, and spherical aberration. The features are unequal effects Fy and different focal length at different parts of the lens. And third is different clarity for the same object at different light wavelengths. So match column 1 with column 2. Please respond in the chat box. I guess it's fairly an easy question. Okay, Rituja responded that it is C. A1, B3, A1, B3, and C2. Okay. Anyone else with any different response or same response? Okay, let's move to the correct answer. Correct answer is C. So astigmatism means that focal length in the x direction of the lens and focal length in the y direction. This is different. They are different. Chromatic aberration. So how to remember? Chromatic means something which has to do with color or colored light, which means different wavelength. So that can be correlated to the third one, that is different clarity for the same object at different light wavelength. So chromatic is related to the light wavelength. So B3, A 1. So such that only one option is there. Now spherical aberration means that at different points of the lens you can find different focal length. They are not the same. So the correct answer is option C. Okay, so let's move to the last question for today. So we have different types of imaging. One such imaging is a bright field imaging and dark field imaging. So the bright field imaging, it uses dash beam, X beam, whereas the dark field imaging uses a Y beam. What is X and Y? X direct beam, Y is refracted beam, or X is diffracted beam and Y is refracted beam, or X is a direct beam, Y is a reflected beam, or X is a direct beam and Y is diffracted beam. So we have two different types of imaging, bright field imaging and dark field imaging. When you use some kind of a beam, we get bright field imaging. When you use some other type of a beam, you get dark field imaging. What is what are the different types of beams, X and Y? Okay. Pratiksha goes with D. KP Rao goes with D. Others? Okay. Let's move to the answer. Correct answer is option D. So this is how the bright field imaging looks like. It uses a direct beam, whatever beam which comes from the source, it is using that. Dark beam or dark field imaging, it is not using the direct beam, it is using the diffracted beams. Then that's how you get the dark field imaging. So this is how the dark field imaging looks like, and this is the bright field imaging looks like. So, yes, that was the basics of microscopy. So, next we have one more week of microscopy. In that, we will discuss more about more concepts about scanning electron microscopy. So, this week it was more about the optical microscopy, the basics ones. So, that's it for this week. I already remember about the request for assignment 6 last few questions discussion. I'll inform the other teaching assistant as well. We'll discuss it in the class. Anything else, please let me know, or else we will meet in the next week with the new topic.